morning, afternoon, evening, as the case may be, to all of you. So this session we have two talks on K3 and BPS states. The first speaker is Taormina, who will tell us about Mathieu Moonshine, quarter BPS states at the Kummer point and nearby. Please, Anne.
Yes, thank you, Samir, and thank you to the organizers of this online workshop. I mean, it's a pleasure to be here. Would have been nicer to be in Japan, of course, but we all know that it's just impossible at the moment. So this talk was presented last week at another virtual workshop. So those of you who were attending last week might find it a bit repetitive, of course. So that's a warning at the beginning. The topic of this workshop are number theory, strings, and quantum physics. And therefore, I will start with a little preamble and the motivation for this work that has been done in collaboration with Katrien Wendland, who will talk after me and will emphasize certain of the things I'm going to only brush upon this morning. I will set the scene, so remind you of the superconformal field theory in which we operate in this context, and then introduce loosely generic and non-generic K3 theories. And again, Katrien will be much more detailed about that. And then look at a particular class of superconformal field theories, which are called Z-orbifold conformal field theories. And here it's a little bit of a shortcut because I really mean Z-orbifolds of toroidal conformal field theories. So it's a little bit of a mouthful, so I left it out. And then I will conclude, give you a postulate, and the message is that the story of Mathieu Moonshine is far from over, certainly from the string point of view, if only that aspect of things. So the paper mostly directly related to this talk is the first one listed there, which is SU2 channels, the cancellation of K3 BPS states. But of course, we take our inspiration on the series of papers that we have written since 2011 or so, briefly after the discovery of the so-called Mathieu Moonshine that I will refresh your memory about for those who are not really working on that area. But before any of this, let me just throw at you a few particular functions that the number theorists in the room will probably recognize, especially after attending Atish Dabolkar's talk yesterday, where he spent a little bit of time explaining certain aspects of mock modular forms and mock theta functions. So a prominent object here is the Appel-Lurch sum, right, which is written as mu of tau and z, where tau is a complex variable with imaginary part positive. I will later on use the variable q, that's very usual, to set q to be e to the 2 pi I tau. And that's an infinite series, which doesn't transform quite like a weak Jacobi form, which is a nice function which has elliptic and modular properties, but you can complete it by some real analytic part, and then it becomes modular. So that featured prominently in Sanders-Weger's thesis, as Atish told us yesterday already. So this Appel-Lurch sum has these elliptic properties, which are listed here in the top line of the first box, and also has a certain behavior under the modular group. So this is under the T generator. Under the S generator of the modular group, it doesn't quite go back to itself, but there is a correction term there, which is a model integral. Now, the first time that I met the Appel-Lurch sum was in the work of Polishchuk in 1998. It was a very nice paper. And then at the same time as Weggers was developing his thesis, unknown to us, and by us I mean Semikatov and Tipunin with myself, we actually derived the modular behavior of what we called at the time the Apple functions. So there is a striking similarity between the two works, except that, of course, Weggers went much further and developed the general theory, while we were more interested in a specific type of Apple functions that come into characters of superconformal characters. Right, so in the second box there, I've written for you functions that will also appear in the talk. The first two in blue there, see, the first one is proportional to the Apple sum. So already you know that under the modular group, something interesting and not as straightforward as you would imagine happens. These two functions, when you sum them together, you get, you sum them as a factor 2 to be fair. So you take the second one plus twice the first one, and you see that the mu behavior disappears, and you get an object that I've written in red here, okay, which is not quite in the box because as we will see later, these functions have a very specific meaning in conformal field theory, but it's still quite a handy notation, because that last expression here is actually a family of function which depends on a real parameter h, provided that h is strictly bigger than 1/4. So altogether in the box we have an infinite number of functions, but if we were allowing ourselves to take h is equal to 1/4, so the lower bound, then we would get this function written in red there. Okay, now the notation that I will use is that a certain subclass of functions from the third category here, with h being a positive integer, so here plus 1/4, okay, is by definition q to the n times this object here. Okay, so, and I like to write it and isolate this chi tilde of r tilde. Okay, so these are just mathematical functions. And now, if we take a very specific linear combination with an infinite number of terms here, you see these are the two functions in the second box, and then the ones that I just described here, and we sum from 1 to infinity. And it turns out that this function here is a weak Jacobi form of weight 0 and index 1 for the number theorist. And what we will be interested in later is actually this infinite sum part. Now, it turns out that the coefficients a sub n there are integer, they are even, and all this has been proven, and we can find an expansion in the variable q, and remember that q is e to the 2r pi tau in this game, and you can calculate quite far, and you find these magic numbers 90, 462, 1540, and so on and so forth. And for many years, these numbers were mysteries to us until 2010, when Eguchi, Oguri, and Tashikawa made the connection between these this sequence of numbers and the dimensions of representations of a sporadic group, which is quite huge, which is the Mathieu 24 group. And it's a proeminent group in the construction of the monster group, which is the largest of the sporadic groups. And this has remained the connection between that group M24 and the context in which this weak Jacobi form appeared is still not resolved. We don't know. Mathematically, it was proven by Terry Gannon that we are really talking about representation of M24 and not, for example, another sporadic group, which is a subgroup of M24, which is called M23. So from the mathematics point of view, a little bit of the veil has been lifted, but we still don't know what the role of M24 is in the context that I will now describe. A little parenthesis here is that hidden in this infinite sum there is actually a weakly holomorphic Mach modular form of weight 1/2 on SL2Z. And this has been developed by Zaghi and collaborators, and Samir, Atish, and Don have a paper, an extensive paper for physicists and mathematicians, where this Mach modular form, among others, appears. So if you're interested to learn more about them, it's a good starting point. Right, so the motivation for this talk is that there is a link between Mathieu Moonshine and so-called K3 theories that I will define in a minute. Now, there should be a vertex operator algebra that underlines the Mathieu Moonshine. That's already hinted at by the work of Terry Gannon, and I think everybody else agrees that it would be nice to construct that vertex operator algebra. So what we do here is not solving the problem, but it's a preparation for the construction of such a VOA, we hope, on the generic space of states of K3 theories. Now, it is known, it's been known since 2012 through a very nice paper by Gabardillo, Henegger, and Volpato, that M24 itself is not the symmetry group of any K3 theory. Now, this is a little bit different from what we are used in physics, that we have a symmetry group, and generally the symmetries, we see them at the level of the partition function, for example. Here, M24 doesn't act on the partition function, it acts on the very specialization of the partition function, and we will come back to that. So if this has nothing to do with Mathieu Moonshine, it's still interesting to study the generic properties of K3 theories per se. So as always, nothing is ever completely lost. Right, so let's work towards the definition of a K3 theory. First, to set the scene, I remind you of what my assumptions are of a two-dimensional Euclidean superconformal field theory, which is unitary. So we start with a conformal field theory, and we assume that there is a world sheet supersymmetry, which is 2,2. So the meaning of this means that we have two generators of supersymmetry, world sheet supersymmetry on the anti-holomorphic and on the holomorphic side. So this is the left and right movers of the string. And on top of this world sheet supersymmetry, we also have space-time supersymmetry. And this one comes about because of the existence of a U1 current in the n equals 2,2 algebra that underlies this theory here. So this U1 gives rise to an operator which is called the spectral flow operator, which depends on the central charge. Now here the central charge left and right is the same, they're identified here. And this spectral flow operator allows you to interchange bosons and fermions of space-time. Now, the space of states of this theory is a unitary complex vector space, which has two sectors, the Neveu-Schwarz sector and the Hamon sector. And in these theories, the two sectors are isomorphic, but still, of course, they are very helpful, both of them, and they have to be included. The U1 current in this superconformal algebra on the holomorphic side is at least its zero mode is J0. Of course, the current has an infinite number of modes. And then this is its anti-holomorphic counterpart. And in describing what comes later, it's important to actually consider a linear combination of the zero mode of the energy momentum tensor of the theory. So that's the zero mode of the Virasoro generator, and shifted by half the U1 zero mode. And these are commuting linear operators, self-adjoint, diagonizable, and T0 and T0 bar are positive. The spectrum of J0 and J bar 0 lies in the integers shifted by the central charge divided by 2. That's one description of it, as long as you are in the Raman sector of the theory. Okay, so such theories have a partition function. It has several terms, but I concentrate on one which is called the Untitled sector, which by definition is given by a trace. And here you see an S, which means supertraced here. And I'll explain what I mean by this. The variable Y here is by definition e to the 2 pi I z, where z is a complex number we introduced before. You see the effect of the holomorphic and the anti-holomorphic sector here. And this trace actually counts the states in your theory as far as this R tilde sector is concerned. The supertrace means that you have to think of a trace where you insert an operator which is -1 to the J0 minus J0 bar, which you can interpret as a Fermion number here. And it basically, it counts states with a sign depending on whether they are fermionic or bosonic. By going from the top line to the bottom line here in the box, you see that I've changed the space on which I take the trace. This is a little bit of an artifact here, in the sense that you can go from one to the next precisely by using the spectral flow. So these two expressions are two ways to express this partition function. Now, that partition function in that sector is invariant under shift of the elliptic variable by 1, and that imposes the spectrum of the difference of the U1 zero modes to be an integer. And on the other hand, the shift by 1 of the modular variable tau imposes that the spectrum of T0 minus T bar 0 is an integer, right? And we also have the modular behavior of this function, this partition function, which is summarized there. Right, so from that partition function, we now construct an object that you see bears the same type of notation as what I introduced at the very beginning, except that here you have the letter capital D instead of 2 that I had there. So it's a slightly more general object. And remember that capital D is related to the central charge by the formula C equals 3 times D. And D is interpreted as a complex dimension here. All right. And what do we do? Well, the S of the supertrace has gone because I've explicitly written it with the -1 operator to the J0 minus J0 bar. What you see here is that the Y bar dependence has gone. So it's been projected to 1 if you want. And I am left in principle with the generator Q bar to the T bar 0 from the anti-holomorphic sector. Now, it turns out that because of supersymmetry, this trace boils down to just looking at summing over the states in the kernel of this T bar 0 operator, right? So effectively, the dependence in tau bar, which is hidden in Q bar, is very much reduced to the zero modes. And then there is even more you can do to reduce the space on which you trace, because there is a pairing of bosonic and fermionic states, and because they are counted with different signs at this level, they disappear from the trace. So if you really strip this expression to the bones, actually you end up tracing over a space of what we call the space of generic states. So it's the generic space of states. All right, now this object is called the conformal field theoretic elliptic genus of the n equals 2,2 superconformal field theory you're looking at central charge 3 times d. And a beautiful property of it is that it's invariant. It's an invariant of all these theories. So because it's an invariant, then you have the possibility to approach it from different vantage points. So from different theories, you will always get to the same object. Now, something I'm not going to talk about, but I'm sure Catherine will, is that all this was done from the conformal field theory point of view, what I just explained, but certainly for K3 surfaces, so not just any compact Calabi-Yau D-fold, but for K3 in particular, the elliptic genus that is called the complex elliptic genus that was constructed by Hirzebruch and also by Witten, that I've just written here for reference here, more later by Catherine, is actually coincides, is the same as the conformal field theoretic elliptic genus. So there is a constant interface between field theory and geometry in all the works that we are doing, and that makes it very rich as a structure. Now then, we can very now easily define what a K3 theory is. So it's a two-dimensional superconformal field theory. Now the central charge is 6, so the complex dimension D, capital D, is 2. And the conformal field theoretic elliptic genus is given by this very nice and compact formula that you saw in Atish-Stokes as well yesterday. Okay, the θ2, θ3, θ4 are Jacobi theta functions. There is a factor 8 there. It's a normalization, but I told you that there is a link between that object and the geometric, the complex elliptic genus. And in particular, if you put z equals to 0, here we have A times 3, which is 24, which is the Euler characteristic of a K3 surface. So that's the very easy first point to convince you that there might be a link between the geometry and this elliptic genus. And of course, that function there, if you dig into it and if you do a Q expansion, then you can reveal other topological invariant of K3 surfaces. So that's very nice. And we know from the very second transparency that when D equals 2, I wrote for you this linear combination of functions that we calculated back in the 80s with Eguchi. So you have now two expressions for the same object, one being very nice and the modular transformation, and this one, which should be equally nice, but made up of building blocks that certainly have challenging modular properties, let's put it like this. So the nonlinear sigma models on K3 surfaces that you've obviously heard of many times are examples of K3 theories. Now, as far as I know, it's not been proven that all K3 theories are of this type, are nonlinear sigma models on K3, but there are no, to my knowledge, examples of K3 theories which are not. So that's right. Something I didn't say so far, and I should have, is that I started by talking about n equals 2,2 superconformal field theory. And suddenly in K3 theories, we have the K3 surface coming in, and we know that actually the symmetry should be n equals 4 because there are 3 complex structure on the hyperkähler manifold. So what I omitted to say is that this spectral flow operator, and that was responsible for the space-time supersymmetry, is an operator which depends on the central charge. And it turns out that for central charge c equals 6, then you generate operators which have the right conformal dimension, i.e. conformal dimension 1, to become currents, so extra generators of the n equals to 2 superconformal algebra. So the symmetry is enhanced in the case c equals 6, and instead of just having a U1 Kac-Moody algebra as a sub-algebra of your superconformal algebra, you have a full SU2. So we have the J0, and then we have J plus and J minus. And this becomes apparent here in this list of commutation and anti-commutation relations between the generators of the n equals 4. So that's the holomorphic sector, say. So the bar here doesn't refer to anti-holomorphic variables, generators here. It's just the notation that I've used over the years. So the hints of the SU2 are obviously into the commutation relations of the raising and lowering operators here. So this is an SU2 affine, which is embedded in that structure. The sigmas are the Pauli matrices. And depending on the moding of the generators G and G bar, which are the supercharges, you have a Ramond-Neveu-Schwarz sector. And I've represented here a little bit how these operators, the zero modes of these operators act on any state of the representation. So black is an any state. So to read this little cartoon here, we read the SU2 carton generator charge, so the J03 if you want here, on the red axis here. And we know that if we act with the ladder operator, the step operator plus here, we increase the isospin of this black state by 1. If you act with G02 and G bar 01, you increase the isospin by 1/2, well, I call this the isospin. And then if you act with G01 and G bar 02, you decrease by 1/2. Okay, so that's the rule of the game. Now, if the black dot happens to be a highest weight state, which I represent here with a green dot, okay, now by definition of a highest weight state, you can't allow the U1 charges to be higher than whatever you start with for the highest weight state. And therefore, you have to set the action of G02 and G bar 01 on the highest weight state to also be 0, as well as J0 plus, okay? So, however, you can act with G01 and G bar 02, that's perfectly allowed, and with J0 minus. And if you do so, and if the result of acting with J01 on the highest weight state is non-zero, in the sense of if you calculate the norm in, using the inner product of your Hilbert space, if you calculate the norm and the norm is non-zero, then you would have what is called a massive representation or a long representation or non-BPS representation. Now, if on the other way, the norm is 0, then you still have a representation available to you, but this time it's either called massless, short representation, or BPS representation. So when I talk later on about BPS states and so on, basically refers to the fact that here I've set G01 on the highest weight state and G bar 02 on the highest weight state to be 0.
Sorry, I have a question.
Yeah.
Maybe 2 slides ago, you mentioned that the Q expansion of the elliptic genus.
Yeah.
Maybe, did I misunderstand? Did you say that it has a geometric interpretation of the Q expansion as well?
Well, if you, yes, you have, well, you have to be a little bit more, let's say, detailed about this. If you allow yourself to shift the variable z in the elliptic genus by a certain amount in the direction of the lattice, yes, then you Q expand, then you will discover the ear subhook signature or the A roof genus. I mean, so there are not all of it, just certain.
Oh, the A genus. Okay, I see. But not all the coefficients, just certain of these.
No. Yes. Well,
okay.
There may be more, but who knows? I mean, all these years back, I remember that one of the first motivation to look into n equals 4 was actually to try to discover more topological invariant of K3 surfaces. But I mean, we didn't succeed. But I mean, I remember many years ago that yeah. So there's a lot of geometry going on, and as I said, you may learn a little bit more about that in Catherine's talk.
Okay.
Okay. Right. So I've said there was an n equals 4 superconformal algebra in this game. So these functions that I introduced at the very beginning happen to be the characters of irreducible representations of the n equals 4 superconformal algebra. And in this sector, which is circled with a dotted ellipse there, we are not going to talk about today because it's still very much not clear how to really interpret this. I mean, yes, there are some hypotheses that has to do with virtual representation of M24, but we don't really have a good feel, or I don't, of what this sector means. And we will concentrate on the sector where we sum an infinite number of these characters in blue. Now, these ones are the massive characters. Okay, so they correspond to the representations where you can act with G01 and G01 and G bar 02. Okay, so we need a definition now. Is that when we look at this expression, it's a little bit hidden, but actually it comes from a specialization of the partition function in the R tilde sector. And a partition function starts by being quadratic in the characters. So the full partition function would have a massless and a massive linear combination on the left, and a massless and massive linear combination on the right. But because we are taking the elliptic genus here, as I told you that there was a projection on the anti-holomorphic side, say, and what you are left with are some memory of the massless sector, right, which is basically a number. Okay, it has to do with the Witten index of the representation. So in the 20 and the 2 there, in hiding, we have the Witten index of the representation, and the quarter BPS states that I'm interested in today are encoded in this infinite sum. And see that here I've introduced, and I already written it before, but maybe not highlighted it then, that the function a of tau is the sum from n equals to infinity of a n q to the n. Okay. So this object here in itself is not an n equals 4 character. You have to include a power of q here with n strictly bigger than 1 in this case, in order to see the n equals 4 character. And that's a little subtlety there. So as we said before, this counts the BPS states with signs. Okay, it's an invariant on the moduli space of K3 theories. And because of this counting with signs, there's, in many theories, there is a cancellation of states within the elliptic genus, and therefore you don't see it in the elliptic genus because they've been cancelled. So somehow the elliptic genus knows how to cancel pairs of bosons and fermions, and still at the end organize what is left over as representations of M24, which is quite a remarkable thing that we don't really understand fully the mechanism of. And this work was actually to zoom in and look at all these states that are counted by the elliptic genus and see if we can understand what the elliptic genus is doing. Okay, and we have partial success with that. So here, vocabulary, generic and non-generic K3 theories. So in the generic theory, there is no cancellation in the elliptic genus. So all the states that are eligible to be counted are counted without anything disappearing, okay? Now, in a way, it would be nice if we could study the link with M24 starting from a generic point of view. The problem is that there are no known theory explicitly. So that's a showstopper, really. So we have to look at non-generic K3 theories. And one class of them is provided by the Z-orbifold conformal field theories, the toroidal ones. Okay, and that's nicely studied. As we will see, it's also linked to geometry in a very helpful way. And another plus point is that the spectrum of generic states for all these Z-orbifold conformal field theories is the same. So you can look at one and then you have it. You have certainly a lot of information for the class. Now, the minus, as we saw, is that we have to deal with cancellation in the elliptic genus. Now, the fact that there are no cancellation in a generic theory was already explained in a paper by Catherine in 2017 that I think she will come back to, and also in work by the mathematician Song, right? So this is a very nice reading and certainly gives you a geometric perspective on everything I say here.
Can I ask one more question?
Yeah.
Just to clarify some notation, when you say Z2 orbifold CFTs, do you mean that you write K3 as T4 mod Z2?
Yes.
Okay.
Yes, I'll explain this in the next transparency.
Okay.
Yes, exactly. Exactly. Right. So in a non-generic K3 theory, and this is introducing some notation, I have the states of the space of BPS states, quarter BPS states here, which is written as an infinite sum. And then the space here is the space on which the n equals 4 superconformal algebra acts, so representation of n equals 4. And the Hn, on the other hand, is dealing with the representation of M24. And M24 commutes with n equals 4. So that's the reason there of this notation. And the full space of quarter BPS state in the K3 theory, we are going to call it H hat. Okay, so what I'm saying here is that in a generic theory, H hat is equals to HPPS, but if it's non-generic, then HPPS is a subset, a subspace of H hat. So for Z-orbifolds, yet to be defined later, the numbers that you read from the elliptic genus are the ones I presented in the second transparency. But if you look at all the states that are present before cancellation, you see that you have more. So for example, at level 1, which is one level where we will concentrate, and we will also concentrate on level 2, you see at level 1 that there are 12 states here, 6 fermionic and 6 bosonic that disappear from the counting. So I'm afraid I still have to introduce a little bit more notation, is that because in the non-generic theories, we know that HBPS and H hat BPS don't coincide. I'm going to call H plus the remaining states, the one that cancel, so H plus here. Now there is nothing a priori that tells us, and there shouldn't be, that tells us that these excess states here transform as representation of M24, right? So M24 is, as far as we know, related to the HBPS part. So the question that we asked is, what is driving this cancellation? And for that, we had to be quite specific. And here we go.
I can ask a question. Sorry,
Yeah.
please. No, please
go ahead.
No, you can go ahead.
I just wanted to clarify something about the notation in the previous slide. So is it correct that HBPS is an invariant of moduli space and H hat BPS is really a function of the moduli? Is that the right way to think about it?
Yes, HBPS is an invariant, yes, and yes.
And H hat is actually a function of the moduli.
H hat.
In the big box, in the middle box. There you go.
Yes. So yes, so here, yes, because I mean, the only thing which is invariant sits in HBPS. So if HBPS coincides with H hat, then obviously it's invariant, yes. But for non-generic theories, the number in excess here depend very much on the point on the moduli space. It turns out that for all Z2 orbifold is the same number. But if you take Gepner models, for example, then the numbers that cancel vary from one theory to the next.
Thanks.
So I have a question too. In the cancellation between A and A roof or A hat,
yeah.
So the first and second terms, they're like order 10 or something, but the third one is like order 400, and the fourth one comes back to whatever. So what's going on at n equals 3?
Well, I mean, I don't know what governs the size of the difference between the two. I mean, I don't have a big insight. I mean, my talk is about understanding how these states come, but yes, I don't have an answer to that. And it fluctuates because you almost go to nothing. You'll see more a little bit, hopefully, in the talk. Yes, oof. Yes. So hopefully you see a little bit more, but ask again if you're not satisfied.
Okay.
Right. So these Z2 orbifold superconformal field theories are, well, sorry, not are. And here, very, very briefly, I give you what I mean by this. So we take a toroidal superconformal field theory at central charge 6, and we mod by Z2. And this construction is induced by the Kummer construction of K3 surface. So this is really the link, a link with geometry here that we exploited a lot. And that Kummer construction takes a torus based on rank 4 lattice, okay? And then we mod by Z2, and we take the minimal resolution of this orbifold torus in order to construct a K3 surface. So that's the link. The partition function of orbifolds has an untwisted and a twisted sector. So basically the untwisted sector allows you to only keep the states from the original conformal field theory before orbifolding, only keep the states which are invariant under the orbifold group. And then by doing that, you truncate your initial theory, so the modular invariance is lost. So you have to add twisted sectors in order to recover the modular invariance of the full partition function. Now, the elliptic genus is a specialization in this case, like in general, like we said, which is expressed here. And I've done something else here, is that I've gone from the object that I've talked about before, which we had in the talk, shifted the variable z by a torsion point here, tau plus 1/2, in order to reach the so-called elliptic genus in the Neveu-Schwarz sector. So we see here the leftover of the projection in the anti-holomorphic sector, Q bar -1/4, together with some numbers that are hidden in E and S. Now this E and S, it's a very well-known decomposition that was certainly exploited in a paper by Gabriel Carrer and Paul. So we use their notations here, which gives the generating functions for BPS states in the untwisted sector in red and the twisted sector. Now there are 16 twisted sectors here because this orbifold construction has 16 fixed points, or 16 singularities. And in terms of functions that are of the same type as the function A of tau that I introduced before, which counts, the number of states, this elliptic genus in the Neveu-Schwarz sector, you see that the numbers have changed here a little bit. That's normal because we're in the Neveu-Schwarz sector and we had shifted the variable Z. In the sector of interest to us, which is the massive sector, okay, the contribution when you reorganize this top expression in terms of characters of n equals 4 can be expressed by a sum of 16 d of tau plus c of tau minus 2b of tau. And okay, so we know that there are cancellations in these theories, and what we wanted to understand is how can we refine the information that we have in this bracket here in order to really put our fingers on the states that disappear. And for this, we used two steps. We used insight from symmetry surfing. That is the program we developed over the years. And we also used a free fermions representation of the n equals 4 algebra. And of course, we used this free fermions to construct the states in question explicitly. But we really explicitly used global SU2 actions on these fermions and their superpartners, okay, in order to have a little bit more information about the classification. Now, I don't know how much time do I have, Samir?
Let me see. You have 10 plus 13, 14 minutes, but yeah, it's a little bit.
Okay. I started a bit
You
late.
also have 15 minutes after that for questions, so you can eat into that a little bit.
Okay. So you see, I'm on page 13 here, but I mean, yeah. Okay, so I said that in the first step I would use insight from symmetry surfing. Now, of course, this would need another talk to explain what this is in detail, but let me show the parallel between the construction of Kummer surfaces and the Z2 orbifold SCFT on K3 a little bit more. So we have already talked about the fact that there are 16 fixed points in the Kummer construction, and this corresponds to the 16 twisted ground states alpha beta that we have in the Z2 orbifold. Now there's a group of geometric symmetries of the K3 surface X here, which we inherit from the underlying torus, and this group acts by permuting the fixed points of the construction here. And in the conformal field theory, the group of symmetries, which is also induced by the underlying conformal field theory, toroidal conformal field theory, permutes the twisted ground states. So that's one aspect of the action of this group. And because there is an action on all these 16 ground states, if we calculate the sum with coefficient 1s of all these 16 ground states, and we act with the GX group, then of course we have an invariant. Okay, and this echoes a vector which is constructed in the lattice that comes into this symmetry surfing program. And this vector, which we called E, is the sum over all the labels of a hypercube, F2 to the 4 here, of EA. So okay, so I don't want to go into the details of this by lack of time here, because we don't really need this as such here. What's important here is that there is an orthogonal complement in the space of twisted ground states, which are 16 of them. So we have a 15-dimensional orthogonal complement to this diagonal state there. And what we discovered in 2015 is that this at level 1 now, so when n is equal 1 in the expansion that we saw in the elliptic genus, we had 90 states, remember? An was 90, and that's twice 45 because the evenness of these coefficients has to do with the fact that you always have the representation of M24 and its complex conjugate when it's a complex representation of, or twice the real representation, okay? So we saw that this just brings to us a 45-dimensional vector space of generic quarter BPS states. Now, what group is acting on this? Well, this is the magic of the symmetry surfing program, is that although each K3 surface and K3 theory, K3 theory will have a group of symmetries which is much smaller than M24, the program allows you to justify the action of a larger group. So it's a collection of all the geometric symmetries, which we call the octile group. Now, the octile group is not M24, it's a maximal subgroup of M24. Okay, so, and it's actually not in M23. So although each GX by Mukai's theorem is a subgroup of M23, okay, the symmetry surfing program allows you to go a little bit further, and it heavily relies on the lattice technology, okay? And we have this octile group. And this octile group acts on the 45-dimensional vector space, okay, which is built on the orthogonal complement of alpha diagonal. So we want to try, and Gabardine and Keller and Paul really did that in a nice paper.
Oh, sorry, I have a question. So,
yeah.
So you said that not all the M23 can be seen from symmetry surfing. It's
no.
Yeah, it's a little surprising. I saw that the M23 is a classical symmetry, so somehow I saw that it should be reflected, but maybe that's not true.
Maybe I don't know if you I don't know exactly what you understood of what I said. Maybe I didn't say it clearly enough. So what I'm saying is that each group of symplectic automorphisms of K3 surface, okay, is a subgroup of M23.
Okay.
So if you take any K3 theory with a fixed K3 surface, then you will get a group which is a subgroup of M23.
Okay.
Okay. But now the symmetry surfing program, which of course is a bit of a black box today, allows you to transcend a little bit this picture by collecting different GXs from different K3 surfaces. You collect all the generators together and you look at what group you generate like this. And that group is the octal group. So the octal group is not the symmetry of any K3 theory.
I see. Okay, so if you choose to pick up a particular K3, then you only get some subgroup of M23, but never the full M23.
No. No. It's a subgroup. Yes, this is Mukai's theorem. Is it? I don't think you get to M23, do you? No.
Oh. Okay, thank you.
Okay. So, right. So based on these insights, it makes sense to actually refine the space of quarter BPS states here into a component which is what we call orthogonal. And this orthogonal now, it's just the 15-dimensional space, which is orthogonal to the diagonal direction of in the twisted space, and whatever is left over within HBPS. And then we still had these excess states that cancel. So the step one is actually to recast HBPS as the direct sum here of H_perp and H_rest. Okay, and the beautiful result, as I said, from Gabriel, Keller, and Paul, is that with very smart group theory arguments and representationary arguments, they managed to conclude that the octet group acts on this space. Okay, and at all levels. So we already at level 1, H_rest happens to be 0, empty. Okay, but at level 2, then there is something there, and they've managed to show that at all levels, not just at level 2, then we have this action. So in a way, it helps with the symmetry surfing program. So, however, there is no construction of these spaces to date at level n bigger than 1. So that's not been achieved yet. Now, Catherine, in her paper of 2017, explained to us that under the formation of the generic K3 theories, all the quarter BPS states that were counted by U, L equals 1/2. So this, remember, entered into the elliptic genus in the untwisted sector. That's what I call 2BN here. And she tells us that all the states in there are lifted. Okay, so they're not generic. And we also have another excellent piece of information coming from Keller and Zadeh, where they looked in detail at the n=1 level, and they deformed one of these, well, they deformed the Z-orbifold conformal field theory in several directions. And they show that if you deform along the diagonal direction I was talking about, then the orthogonal space of states remains BPS. Okay. Now they didn't just take the diagonal direction; they looked in the directions of other single moduli as well, and each time they find that the orthogonal space of state here is such that it remains BPS. So this is again a beautiful result. At level 1, of course, the rest, as I said, is empty. So it would be very nice to do a similar calculation at level 2 to see if what I'm going to say in the next few minutes is going to be correct or not. So this is a summary of what I said before, but now written in terms of these generating functions, Bn, Cn, and Dn here. So the 16 twisted sector now split into one which has to do with the diagonal part, and then the 15 others. And I've arranged the untwisted contributions here in red, but in such a way that you see now that the full number of state here has an addition of 2Bn and a subtraction of 2Bn. So you see, this is not the elliptic genus because it's the total number of quarter BPS states not counted with sign. So you don't see a minus 2Bn here, you see a plus 2Bn. And the correspondence with the notation Hn_perp, H_rest, and Hn plus is given here. So that's a first little progress in understanding the elliptic genus. And now we would like to really see if we can put a little bit more structure on this part here, so on these ones here, because here we have to take 2Bn states from Cn plus Dn, but we don't know if they all come from Dn, they all come from Cn, or if they come from a little bit of both. Okay, and that's really the question. And we have a postulate that actually they all come from Dn, okay? And this is based on this second step, which uses the free field representation of n=4. Of course, all this is rooted in the fact that we have a torus at the beginning. So we have two Dirac fermions and they're super partners. So can think of this as generating the translation on the along the sides of the torus that we are looking at. Okay, so this is quite well known. And we want to construct an SU2 action that commutes with the n equals 4 to provide a better classification of these functions B, C, and D. And here is the rule of the game. So this SU2 geometric actually is not completely out of the blue. We talked about the geometric symmetries a minute ago of the K3 surfaces, yes. And this geometry group, geometry symmetry group of the Z-orbifold has a linear part. It also has a translational part, okay? But the linear part is actually contained in the SU2 geometric. That's why we call it SU2 geometric here. And the action on the space H rest for H plus is given by these rules here. So the fermions and the bosons here transform as doublets, and the SU2 geometric holomorphic, and as singlet under the anti-holomorphic, and the anti-holomorphic fields vice versa, okay? The vacuum state of the theory and the diagonal twisted ground states transform as singlet, and the product SU2 cross SU2 bar. And this is a little bit of a summary of how these fermions and bosons transform under the affine SU2, which is within n equals 4, and under this global SU2 geometric there. So once you have these rules, you can look at the partition functions that is present in the elliptic genus. You have information about the quantum numbers. You introduce a new complex variable to trace the SU2 geometric and not just the SU2 affine. So now it's just a dictionary between these partition functions and the states. And at the end of the day, when you do this, you see that the states in the twisted sector here, Bn, if you remember, at level 1, the black numbers are the number of states. So this is the value of Bn, it's 3, okay? And the purple color here indicates how they transform under this SU2 geometric. So the 3 states at level 1 coming from this untwisted sector transform as a triplet, okay, under this SU2. At level 2, you see that there is only one such state, okay, and you see that these numbers vary from level to level. So it goes from 3 to 1 to 18 to 15. So we don't understand the pattern there, but what we understand is that you can decompose, let's say at the level 3 here, you have 18 states, so you have a triplet and you have 3 quintets. So the upper index is the multiplicity of the representation that you are looking at, and so on and so forth. And then you do the same for the other untwisted sector, but there the representations corresponds to a half integer spin. So we have even dimensional representations, while here we add integer spin. And in the twisted sector, in one of the twisted sector, but it's true of any of them, you also have integer spin representations. So in the count of dn minus 2bn plus cn, the postulate is that they cancel according to the behavior under the SU2 geometric, so that you can only do dn minus states. So we have 2 triplets here under this SU2 geometric. Well, here we have no choice because there is no Cn. This is dH rest, which is 0. So here it's twice 3. So that's, you don't learn the full story here. But if you look at level 2 already, where we have done explicit calculations of states in gory details, you have 1 singlet there, and you have 2 singlets for dn. And since you do dn minus 2bn, then again, they cancel. At this level, you see that again, it works pretty nicely. But of course, as you go on, you have more and more states. And therefore, you start having possibly, if we went further than 4, certainly not calculating the states, because already at level 2 it's quite complicated, but you, after a while, you get an ambiguity, is that you have more SU2 representations available to you than what you have for BN. So it's not perfect, if you want. So the states in H plus, we think, are paired up according to their transformation property under this SU2 cross SU2 bar, and all untwisted states accounted for, which are in CN. So this is was UL0 are generic. So that's our postulate. And I think that because time is pressing, I will leave this to Catherine to discuss, because I know that she had planned to. So I will just conclude. So here you can certainly read it. It's just wrapping up, but telling you what I've said during this talk. Well, thank you very much.
So thank you very much, Anne, for the nice talk. So any questions? Yeah, Abhiram.
Hi, and thanks for a very nice talk. Can I go back to the thing with the A and A hat real quick?
Oh, at the beginning.
At the beginning. So this one would like.
No, it's not here. I just passed it. Here.
Yeah, there we go. Yeah. So it's 90, 102, 462, 466. That's fine. I just want to focus on 3 again. It's 1540 and 1944 here.
Mm-hmm.
You go back to like slide number 18 now.
Okay.
So here, like you take the difference between A and A hat, and the first term is indeed 6. So I think you get it's first term, the A and A hat is 12. I think that you get a 6 plus 6, and the next is 4. You get a 2 plus 2. But the other one, and the number 4 is also 30 plus 30. But here, the delta between A and A hat. So basically, what I'm trying to say is 2bn plus 2bn in red. That matches with the difference between A and A hat, except for the case of 3. Because A minus A hat for the case of n equals 3 is going to be 202 plus 202. And why is 36 plus 36 here? Or is there something strange going on here? I just don't understand.
Okay, well, I'm lost.
Sorry.
I'm lost. I mean, too many numbers too quickly.
Sorry.
So
basically, what I'm doing is I'm comparing A minus A hat, or sorry, A hat minus A, right?
AN minus A hat.
Yeah, A hat minus A, and comparing it to 2bn minus 2 plus 2bn, you know, the one in the lower column.
The one in the bottom.
Yeah. So these numbers correspond to A hat minus A on the nose, except for number 3, which is 36 plus 36 here. But
Yes.
if I try to match that to A hat minus A, that's going to be 202 plus 202.
Right.
So is there something, am I not supposed to compare these numbers, or?
Well, so A hat would be dn plus 2bn plus cn, yes? That's what A hat would be.
A hat would be
Plus 15
plus 15
dn.
dn, right? That would be the
Yeah.
exact same as A.
So that would be A hat, yes? If I would replace here by a plus and add this, then I would get A hat.
That's right. Mm-hmm.
Okay, okay. Now you're saying that if I do dn plus 2bn for number 3, I get 98 plus 18, so that's 116. Okay.
Mm-hmm.
No, plus 36, sorry. 36 plus 98, that's what I get for dn plus 2bn plus cn, okay. And what's the problem, sorry?
Sorry, I was just, I wasn't focusing on that. I was focusing on the lower column, the last row.
I think that's fine. The problem was that it doesn't agree with what you showed on page 2. I think that's
the number doesn't seem to
fit.
Okay, okay. Well, let me just think a little bit while Catherine is speaking, and then I'll come back to you.
Okay.
It could very well be that I miscopied. I thought I was careful, but I mean,
Mhm.
okay, I'll see what's going on. It's probably a typo somewhere.
Mhm.
If
Yeah,
there
this
is a
the one that's like wildly oscillating, and then first line.
okay.
Yeah.
Well, let me just go into the number crunching.
Hey, I have another question.
Yeah.
Well, actually, I shouldn't ask. Does anyone else have a question? Yeah. Please go on. Hikami-san.
Samir, are you talking?
There's a raised hand by Hikami-san. I don't know if he wants to ask a question or not.
Ah, okay.
I want to understand the modularity of B tau, C tau, D tau. Maybe written in 19. Page 19.
Page 19. This one?
Yeah,
Okay.
what is the modularity of B tau, C tau, B and C and D?
Yes.
These functions have some modular property?
Well, well, we don't. You see what they are looking. You know, it's Kazuhiro Ikami speaking. Yes.
Yes.
Okay.
Yeah,
Hello.
nice to meet you again.
Yeah. So you know these functions H3 and H4, for example. You know them well.
Written in, yeah, I see.
And therefore, I mean, we know that kind of linked to the upper Lurch sum as well somehow, yes?
Okay, yeah, thank you.
And therefore, the module, so these objects are a little bit tortured compared to the nice formulas or functions that we usually have, yes? And that's what has proven quite difficult in this condition. So we have, let's say, an empirical proof of this positivity condition by just looking at Q expansions up to high power of Q, and then we see that this condition here is always fulfilled, okay? But we failed to prove it from a, let's say, number theoretical point of view. And we've tried quite a bit because we thought it would be easy-ish, and we failed. So we decided to just throw it to somebody who might have a clever idea or a technique to do this. So maybe you are the right person.
Thank you. Thank you for nice talk.
Thank you.
Okay, other questions? Maybe we have a minute or so. I don't see any other hand. I had one question. This SU2 geometric,
yes.
What is that in terms of the K3 surface itself?
What is it in terms of?
Let's say the K3 CFT or
yes.
K3 surface. Yeah.
Okay. So, okay. So the interpretation I gave, you understood, yes? It contains the linear part of the geometric symmetry groups of K3 surfaces, okay? So you know the geometric symmetry, they have a Z2 to the 4, which corresponds to the translations on the torus, yes. Semi-product with, depending on the lattice that you take, Z2 square or S3 or the tetrahedral group, okay?
Right.
So I'm talking about these subgroups, these being subgroups of this SU2 geometric.
So it's some abstract group which you think of as
yes. So there is something else, but I thought it was correct, but now I have a little bit of a problem reconstructing the story properly. I thought that it might be linked to the SO4 global symmetry that free field representation of n = 4 has. Okay, so and And I thought that I understood that. And in constructing the talk, I got stuck that it's not doing exactly, it's doing almost exactly what I want, but not quite. And I must say, it should be sorted out because it's either or not, but it shouldn't be a difficult calculation, but you know, I failed to reproduce the behavior here. That, see, these two are meant to be a doublet under the SU2 geometric, chi1 plus and chi2 plus.
Yeah.
Okay, for example. And I'm struggling with that in that context, but I don't think it's a big problem. I mean, as I said, that's why I wouldn't want to put it in the talk because I'm not sure. So the safest answer is the one I gave, all right? Mm-hmm. There are questions about this SU2. I mean, at the moment, it's just a bookkeeping device. And of course, it's not completely satisfactory. We have to really understand whether it flies or not. I mean.
Okay, thank you. There are two people with raised hands.
Yeah, I raised my hand again.
It's, well, you're one of the organizers, so you tell me if we should stop or continue.
I just have a very naive question, which is, sorry, continue. Which is, can you do this for K3 being, can you think of K3 now as being T4 mod Z3 and repeat the process?
Well, I mean, we are thinking about that. Okay, so we have a group of women in mathematics. Ida, who is in the room, is part of this. I don't know how far we will go with this. It's not clear that it will bring anything substantially different, but we need to learn this a little bit to progress. So yes, you can do mod Z3 or mod any I mean, Z4 and Z6 or whatever, and you can. It's in the spirit of symmetry surfing. Okay, it's technically involved, so you have to really understand lattices and how they embed into each other. So it's a technical problem. Whether it will bring anything else, we don't know yet.
Okay, thank you.
The other person involved, I should mention as well, is Kasia Bunzink, who is a student of David Gaiotto.
Mm-hmm.
And Ida
okay.
and Mara Ungeranu was a postdoc in Freiburg at the moment. She's a mathematician. And Katrin.
Mm-hmm.
Okay. But it's we are not finished.
Okay.
Okay, so then let's thank Anne again. And